Good morning, students.
Good morning, ma'am.
Okay, very good morning. So in our last class, we discussed about the LCR circuit and some equations regarding with that of the LCR combinations and the resonance condition. So first of all, we can recollect all these equations connecting with this LCR circuit. After that, we can discuss about the resonance. Okay. Then starting with Gauri. What is the equation for calculating the total resistance of LCR combination?
Z is equal to root of chi L minus chi C the whole square plus R square.
Chi L minus chi C the whole square plus R square. Okay, then next question, Dia. Equation for calculating the direction of current.
Chi equal to tan inverse chi L minus chi C by R.
Chi L minus chi C divided by R. Nandana.
Yes, ma'am.
Equation for calculating power factor of LCR combination.
Phi is equal to cos inverse of R by L.
Okay, phi is equal to cos inverse R by Z. Then next question to Vidur. What do you mean by resonance?
If the resistance offered by the inductor and the capacitor will be equal, then the term chi L minus chi C is equal to 0. So
Okay.
the LCR combination circuit will act as resistive circuit.
It is purely behaves like a resistive circuit. So that is what is known as resonance. So resonance means chi L minus chi C is equal to 0. That is the resistance offered by the inductor and capacitor becomes equal. When it becomes equal, whenever the frequency offered by the inductor and that of the capacitor becomes equal, then the resistance offered by the inductor and capacitor become equal. That is chi L minus chi C is equal to 0. Then our LCR combination is purely behaves like a resistive circuit. So that is what is known as resonance condition. So now we are going to discuss some special cases that comes under this resonance. Let us continue with the same topic. Special cases. So we know that the equation for calculating the impedance Z is equal to root of chi L minus chi C the whole square plus R square. This is the general equation for calculating the total resistance offered by the LCR combination, and the total resistance offered by LCR combination is known as impedance of the circuit. Now, if the circuit contains no capacitor, that is, if C is equal to 0, then what is the equation for impedance? Z is equal to, if the LCR circuit, if the capacitor contains no charge, or if we can see if it is C is equal to 0, what about the impedance of the LCR circuit? Z is equal to, if C is equal to 0, does it offers any kind of resistance, which implies chi C is equal to 0. So then what about the impedance of the circuit? Z is equal to?
Chi L square plus R square.
Yeah, chi L square plus R square. So if there is no capacitor is present in the circuit, then the impedance of the circuit becomes Z is equal to chi L square plus R square. Or we can call that such circuit as LR circuit, because here capacitor is not present. So this is the impedance equation for LR circuit. LR circuit. Here there is no capacitor, so the equation for impedance become Z is equal to root of chi L square plus R square. L for inductor and R for resistor. So the circuit which consists only the inductor and R resistor, then we can call it as LR circuit. It doesn't contain the capacitor. Similarly, if the circuit is consists only the capacitor and resistor, that is if the inductor is absent. The second case, if L is equal to 0, then the impedance Z is equal to, L is equal to 0 means resistance offered by the inductor chi L is equal to 0, which implies Z is equal to, what is left? Chi C square plus resistance offered by the resistor, that is R square. Z is equal to chi C square plus R square, root of chi C square plus R square. This is the impedance for, can you name this circuit? Here L term is not present, so it is CR circuit. CR. Circuit which consists only the capacitor and resistor. Here in this case, the inductor is not present. Inductor is absent. So these are the two special cases that comes under this resonance condition, or the special cases of LCR combination. In an LCR combination, if the capacitor is not present, then it becomes LR circuit, inductor resistor circuit. Then we can calculate the impedance using the equation Z is equal to root of chi L square plus R square. In the second case, if the capacitor is not, sorry, if the inductor is not present, then L is equal to 0, chi L is equal to 0, then it behaves like a CR circuit, capacitor resistive circuit. In such case, we can calculate the impedance using the equation Z is equal to root of chi C square plus R square. Is it clear? Okay, now we are moved to the next topic, sharpness of resonance. Sharpness of resonance. Sharpness of resonance. So in sharpness of resonance, we are going to consider a graph between the current and that of the angular frequency. So here we are starting our derivation or explanation by considering the Ohm's law. By Ohm's law, we know that I is equal to, what is the equation for calculating the I by Ohm's law? I is equal to
V by R.
V by R. I is equal to V by R. But here we consider LCR circuit. In the case of LCR circuit, LCR series combination, the value of I is equal to, this is the general expression for calculating the current, I is equal to V by R. But here we are not only consider the resistor, here we consider the case of LCR, inductor, capacitor and resistor. Then the value of current becomes I is equal to, I write the equation if and only if you say the answer. I is equal to
V by Z.
V by Z, because here the resistance due to inductor, capacitor and resistor. According to the general equation, I is equal to V by R, Ohms consider only the resistance offered by the resistor. But here we are describing the LCR circuit. LCR circuit means it consists of inductor, capacitor and resistor. So we need to consider the resistance offered by all these three components. So the equation becomes I is equal to V by Z. Again, we know that I is equal to V divided by, what is Z? Z is equal to root of chi L minus chi C the whole square plus R square. So in an LCR circuit, we can calculate the current. I is equal to V by Z, where Z is the impedance, that is equal to root of chi L minus chi C the whole square plus R square. And what do you think? What about the resistance offered by all these three components? We know that in the denominator, the term consists of resistance. Resistance offered by inductor, capacitor, and resistor. The current and resistor are inversely proportional to each other. So in the denominator, we know that the term entirely consists of resistance. It is offered by the inductor, capacitor, and resistor. So as a total or as a whole, it produces a large resistance. Okay, so in the denominator term, the resistance offered by all these components are large. Then what happens to our value of current? Here in the denominator, we have a large value of resistance. Resistance offered by inductor, capacitor, and resistance. Then what about the value of current? Is it increase or decrease?
Decrease.
It is a decrease, because according to Ohm's law, we know that current is equal to V by R. Current is inversely proportional to resistor. Here we write an expression for current that is formed in an LCR circuit in the same manner. So instead of R, here we are consider the term impedance, Z. And we know that Z is equal to root of chi L minus chi C the whole square plus R square. All these are the resistance offered by the three components such as inductor, capacitor, and resistor. So here in this case, as a whole, the resistance offered by all these three components are large. So it offers a minimum amount of current. So here we are going to draw a graph. When we are consider the current versus angular frequency graph. Here we are going to draw a graph. Take the angular frequency omega along x-axis and the value of current along y-axis. By plotting a graph, current versus angular frequency. From the above expression, it is clear that in the case of LCR combination, in the case of LCR circuit or LCR combination, the resistance offered by all these three components are large. Here in the denominator, we have a combined effect of the resistance offered by resistor, inductor, and the capacitor. Okay, so in the denominator, the value of resistance is large. So we can say that it offers a minimum current. It offers a minimum current. So the graph will be like this. It offers a minimum current. Here in the denominator, the value of resistance is large because it is the resistance offers due to resistor, inductor, and capacitor. Since the resistance is large, we can say that it offers a minimum current. But under resonance condition, what is our resonance condition? What is the resonance condition? Yes, chi L is equal to chi C. Then what is the value of current in the LCR circuit? I is equal to chi L is equal to chi C means which implies chi L minus chi C is equal to 0, right? So that is the first term cancels. Then we have V I is equal to V divided by root of R square, or we can write I is equal to V by R. Under resonance condition, the resistance offered by inductor becomes equal to resistance offered by the capacitor. That is chi L is equal to chi C. That is what is known as the resonance condition. So under this resonance condition, we can say that chi L minus chi C is equal to 0. So what happens to the equation for current? I is equal to V by root of R square. The first term cancels, it becomes 0. So I is equal to V divided by root of R square, or we can write I is equal to V by R. Now what about the value of resistance as compared to that of the LCR circuit? Does it increase or decrease? Under the resonance condition, what happens to the value of resistance? It is decreases, because in the case of LCR circuit, we have a combined effect of the resistance offered by three components. But under resonance condition, chi L becomes equal to chi C. Resistance offered by the inductor becomes equal to resistance offered by the capacitor. So that terms cancel. But under the resonance condition, we have the resistance offered by only one component, that is resistance. So here the value of resistance is decreases. Then what happens to value of current? Current increases. So under resonance conditions, it offers a maximum amount of current. Under resonance condition, it offers a maximum amount of current. So the first graph indicates the graph for LCR circuit. The second one for resonance condition. So under resonance condition, chi L is equal to chi C, or chi L minus chi C is equal to 0. So the first term cancels. So we can say in the denominator, it contains the resistance offered only by the resistor. The resistance offered by the inductor and capacitor cancels. So here the resistance offered by the resistor is only present in the denominator. It offers a maximum current. So here we can write I maximum. Under the resonance condition, the current becomes maximum because the resistance offered by inductor and capacitor becomes equal. So under the resonance condition, the current becomes maximum. We can write I max is equal to V by R. I max is equal to V by R. So this is the maximum value of the current. We can mark the maximum value of current in the graph. Corresponding to this peak, here we get the maximum value of current, and this maximum value of current is obtained for LCR circuit under the resonance condition. Then the frequency corresponding to this maximum value of current is known as resonant frequency. The frequency corresponding to the maximum value of current is known as resonant frequency. It is represented by omega 0. The frequency corresponding to maximum value of current under resonance condition. The frequency corresponding to maximum value of current under resonance condition is known as resonant frequency. It is represented by omega 0. So here we have two peaks. The first one is a smaller peak. It is mark the value of current for LCR circuit. In the case of LCR circuit, the resistance offered by all the three components are present. The second peak we are obtained for a maximum value of current, and this peak is represents for the value of current under the resonance condition. Under resonance condition, the resistance offered by chi L, inductor and capacitor, becomes equal. So the resistance offered by the entire circuit will be decreases. As a result, it offers maximum current. So under resonance condition, we get a maximum current, I max. I max is equal to V by R. Here the resistance is only due to the presence of the resistor. Then the corresponding frequency, the frequency corresponding to this maximum value of the current under resonance condition is known as resonant frequency. Resonant frequency. It is represented by the letter omega 0. Is it clear? Yes or no? Any doubt regarding with this?
No.
Okay. So now we are going to explain the sharpness of resistance, because here we get a sharp graph corresponding to the value of maximum value of current versus the frequency omega 0. We are going to explain the sharpness of resonance in detail. Okay. So the sharpness of resonance can be determined with the help of quality factor. So all of you write the next statement. Sharpness of resistance, sorry, not resistance, resonance. Sharpness of resonance can be determined with the help of quality factor. So sharpness of resonance can be determined or can be better explained with the help of quality factor, can be determined by quality factor, or simply we call it as Q factor. Sharpness of resonance can be determined by calculating the or finding the quality factor or by explaining the quality factor, or we simply call it as Q factor. So now we are going to explain what you mean by Q factor. Q factor is defined as the ratio of Q factor is defined as the ratio of inductive reactance to resistance Q factor is defined as the ratio of inductive reactance to resistance. That is, Q factor is equal to inductive reactance divided by resistance. How we are representing the inductive reactance? Inductive reactance is represented by chi L divided by resistance R, or it is the ratio of capacitive reactance to resistance. Capacitive reactance to resistance. That is equal to chi C divided by R. Sharpness of resistance can be determined with the help of quality factor, or simply we can call it as Q factor. So here we define what you mean by quality factor or Q factor. Quality factor or Q factor means it is the ratio of inductive reactance to resistance, or it is the ratio of capacitive reactance to resistance. Both equations are right. So we can write Q is equal to chi L by R, or Q is equal to chi C by R. So by obtaining the value of quality factor, we can define the sharpness of resonance. So that is what we are going to discuss next. The expression for sharpness of resonance. Sharpness of resonance can be explained by quality factor or Q factor. It is the ratio of inductive reactance to resistance, or it is the ratio of capacitive reactance to resistance. The mathematical expression Q is equal to chi L by R, or Q is equal to chi C by R. Now the mathematical derivation or the expression for sharpness of resonance. In order to derive the mathematical expression for this sharpness of resonance, we consider the current versus angular frequency graph under the resonance condition. So consider the graph, angular frequency omega along x-axis and current along y-axis. Yes,
For sharpness of
resonance, sharpness of resonance. So in the previous case, we consider the two peaks. One is for the current versus angular frequency for LCR circuit, and the second peak is current versus angular frequency for under the resonance condition. So here, in order to explain or in order to derive the expression for sharpness of resonance, we need the second peak, because here we are going to consider the resonance condition only. So consider the graph by taking angular frequency omega along the x-axis and the value of current I along the y-axis. And we know that under the resonance condition, the graph will be like this. We get a maximum peak. The maximum value of current is obtained under the resonance condition. It is marked as I max. And what about the corresponding angular frequency? Frequency corresponding to the maximum value of current under resonance condition is known as resonant frequency. It is taken as resonant frequency.
Omega 0.
Yes, it is omega 0. In order to derive the mathematical expression for resonance, here we consider the graph of LCR circuit under the resonance condition. That is that XL is equal to chi L is equal to chi C. We get a maximum value of the current. It is represented by I max. The frequency corresponding to this maximum value of current is known as resonant frequency. It is taken as omega 0. Then consider a value of current in the upper half cycle of this peak. Consider a value of current in the upper half cycle. Consider a value of current in the upper half cycle corresponding to a frequency of omega 1. We don't know about the value of this frequency. So here we consider that this frequency is equal to omega 1.
ma'am.
Yes.
Say again, ma'am.
Consider a value of current. Consider a value of current in the upper half cycle. Upper half cycle. Consider a value of current in the upper half cycle corresponding to a frequency of omega 1. Consider a value of current in the upper half cycle corresponding to a frequency of omega 1. The maximum value of current is corresponding to a frequency of omega 0. But here we consider a value of current in the upper half cycle, which is corresponding to a frequency of omega 1. And suppose the value of current at this point is taken as I maximum by root 2. This is what is we are taken here. Corresponding value of current is taken as I maximum by root 2. Maximum value of current is represented by I maximum. But here we consider a value of current in the upper half cycle. The value of current is, suppose we consider it as I maximum by root 2. Corresponding frequency of that upper half cycle is omega 1. Similarly, consider a value of frequency, so not frequency, consider a value of current. Similarly, consider a value of current in the lower half cycle, corresponding to a frequency of omega 2. Yes.
Can you say once more?
Okay, similarly, consider the value of current. Similarly, consider the value of current in the lower half cycle. Consider the value of current in the lower half cycle corresponding to a frequency of omega 2. Omega 2. With the value of current is equal to the same, I maximum by root 2. With the value of current, I maximum by root 2. So here we consider two values for current. One is at the upper half cycle, which is corresponding to a frequency of omega 1, and we don't know the value of current. So suppose we imagine that corresponding value of current is taken as I maximum by root 2. Similarly, here we consider the value of current in the lower half cycle corresponding to a frequency of omega 2 with the same value of current, that is corresponding to I maximum by root 2. And here we can say that the angular frequency omega 1, here the angular frequency omega 1 is less than that of the frequency omega 0, because omega 0 is the maximum frequency offered by the LCR circuit under the resonance condition. Here this omega 1 is less than that of the omega 0 by a small amount of delta omega. So here we can write, here omega 1 is less than omega 0 by a small amount. Okay, so omega 1 is equal to omega 0 minus delta omega. Here the angular frequency omega 1 is less than the maximum frequency omega 0 by a small amount delta omega. So the equation becomes omega 1 is equal to omega 0 minus delta omega. Again, this angular frequency omega 2.
Ma'am,
Yes.
why do we take root 2?
Yes, Achyut?
No, ma'am, why do we take root 2, I max by root 2?
That is the condition that we are consider here. In effect, I max by 2 into I max by root 2. That is what is we are taken in our textbook. We are just consider, then only the power factor becomes 1 by root 2 times of its half cycle and all. So this is the general condition that we are taken here in order to solve this sharpness of resonance and thereby deriving an expression for sharpness of resonance. This is what is we are taken inside the textbook itself. Okay. So in order to reduce the power factor by a factor of 1 by root 2, that's why we have taken it as I maximum by root 2. I will give the notes with the explanation why we are take this I maximum by root 2. If and only if we are taken it is by I maximum by root 2, then only at this value, the power dissipated will be equal to half of the LCR circuit. That is why we consider it as I maximum by root 2. Okay, so here the frequency omega 1 is less than from that of the maximum frequency omega 0 by a small amount, that is delta omega. So omega 1 is equal to omega 0 minus delta omega. Similarly, omega 2 is greater than that of the maximum omega 0, maximum frequency omega 0 by a factor of delta omega. So we can write omega 2 is equal to omega 0 plus delta omega. Here the frequency omega 2 is greater than that of the maximum resonant frequency omega 0 by a small amount. That small amount is taken as delta omega. So it becomes omega 2 is equal to omega 0 plus delta omega. Now we are going to subtract these two values of frequency, omega 2 minus omega 1. What is omega 2 minus omega 1? Then omega 2 minus omega 1 is equal to omega 0 plus delta omega minus omega 0 minus delta omega. Or we can write omega 0 plus delta omega. Take this negative sign into the bracket. It becomes minus omega 0 minus of minus plus delta omega. So this omega 0 and omega 0 cancels. We get delta omega plus delta omega. What is delta omega plus delta omega? 2 delta omega. Omega 1 is equal to omega 0 minus delta omega because the first angular frequency is less than that of the maximum frequency by an amount of delta omega. Omega 2 is the second frequency that we are considering in the graph. It is larger than that of the maximum resonant frequency omega 0 by a small amount. So we taken it as positive delta omega 0 plus delta omega. Then in the next step, we just take the difference between these two angular frequency. So we get omega 2 minus omega 1, that is equal to omega 0 plus delta omega minus omega 0 minus delta omega. Then we take this negative sign into the bracket. It becomes omega 0 plus delta omega minus omega 0 plus delta omega. By cancelling these two omega 0 terms, we get 2 delta omega. So here omega 2 minus omega 1 is equal to 2 delta omega. The difference between the two frequencies is equal to 2 delta omega. This expression is known as bandwidth of this LCR circuit under resonance condition. Bandwidth. That is the difference in the frequency between upper half cycle and lower half cycle of the LCR circuit under resonance condition is known as bandwidth. The difference in frequency between upper half cycle and lower half cycle, that is omega 1 and omega 2 respectively. The difference in frequency between upper half cycle and lower half cycle, the difference in frequency between upper half cycle and lower half cycle of this LCR circuit under resonance condition is known as bandwidth. The difference in frequency between upper half cycle and lower half cycle of LCR circuit under resonance condition is known as bandwidth. Then the sharpness of resonance condition can be written as, then the sharpness of LCR circuit is given by sharpness of resonance. Then the sharpness of resonance is given by ratio of resonant frequency, ratio of resonant frequency to that of the bandwidth. Then the sharpness of resonance is given by ratio of resonant frequency divided by bandwidth. Or we can write sharpness of resonance is equal to resonant frequency means omega 0 divided by bandwidth means 2 delta omega. So sharpness of resonance is equal to omega 0 by 2 delta omega, or it is the ratio of resonance frequency by bandwidth. So depending upon the value of this delta omega, sharpness of resonance can either increase or decrease. If delta omega decreases, then what happens? Sharpness of resonance increases. If delta omega increases, then sharpness of resonance decreases. So depending upon the value of delta omega, the value of sharpness of resonance may be increase or decrease. Now, sometimes there may be a doubt can be arise in your mind. That is, in the very beginning of the class, we are discussed that sharpness of resonance can be determined with the help of quality factor, right? Or Q factor. But at the end of the derivation, we get another expression. Sharpness of resonance is equal to the ratio of resonant frequency divided by bandwidth. Both are entirely different, right? So here we want to prove that this quality factor and this equation are exactly equivalent. Both are equal. Sharpness of resonance omega 0 by 2 delta omega and the quality factor chi L by R or chi C by R are equal. So here in the next period we can prove these two equations are equal. Okay, so it's the time we can wind up this session.